All right, now that we've been looking at calculating enthalpy changes using a calorimeter, in other words, doing the enthalpy calculations by gathering experimental data, there are also a couple of theoretical ways in which you can calculate the enthalpy for a reaction. So we'll take a look at both of these. The first one is looking at all of the energies that are involved in the bonds that are in the molecules of reactants and products. So if we, in a minute, we'll take a look at a reaction. Every one of those molecules has a certain number of sigma bonds or pi bonds that when the molecule changes from a reactant to a product, those bonds have to be rearranged. And there's energy involved with that rearrangement. We can use kind of an estimation of how much energy is in a bond in order to calculate out what the actual enthalpy change for a reaction might be. It's a bit of an estimation because you might have something where you're breaking a CC bond in maybe like a molecule like ethane, or you might be breaking a CC bond where what we do is take that ethane and we replace one of the H's with a Br. And since the Br is electronegativity a little different than the hydrogen, it's going to affect how those electrons are shared in the bond. It's going to affect the strength of this CC bond. So even though this is a bond between two C's and this is a bond between two C's, the energy involved in these bonds in breaking them or making them, excuse me, is not the same. So there are slight differences depending on the rest of the atoms that are adjacent to the bond that we're looking at. So that's why we say this is an estimation. It's not the best way to theoretically figure out an enthalpy change, but it works if you don't have any other information that you can use. And then finally, there's another method called Hess's law, and we'll take a look at that one in another video so you can see how that one also can be used to calculate enthalpies. So when we do an enthalpy calculation, we have to take a look at a graph something like this one, and we'll see we have some reactants that have a certain amount of energy. So again, this scale on the side represents energy, and that energy is stored in the bonds in these molecules. So there's two hydrogen molecules here, 2H2, and so there's a sigma bond between these two, and there's a certain amount of energy stored in that bond. In the oxygen, there's one oxygen atom. It is a oxygen double bonded to another oxygen though. So there's a sigma bond and a pi bond inside that, where over here there was just sigma bonds holding the two H's together. Now, as this reaction proceeds, these reactions will collide. They will rearrange. That's what happens during the transition between reactants to products. And when they rearrange, they form new bonds. And so over here, we're going to make two water molecules. And the new bonds that are formed are not any that were there before. So they're different kinds. And they're sigma bonds between an O and an H. And there's two of them in every molecule. Okay. So what this graph is showing is that there is more energy stored in these bonds than there is in the bonds that we end up making in our products. And so that is our change in enthalpy. The difference between the energy stored in the bonds of the products and the energy stored in the bonds of the reactants gives us our enthalpy change. That's that energy that's, well, in this case, lost. So the enthalpy change is exothermic because the products have less energy than the reactants. And so that enthalpy change is a loss of energy. And of course, when you light hydrogen and oxygen on fire, they go boom. So that would give us that exothermic loss of energy. Okay, so what we want to do is look at how do we use what we know about these bonds to calculate what this change in enthalpy is. So just to go back over that a little bit, during the reaction bonds are broken. So that's our first idea to remember, that whatever we have as reactions, we can imagine those being broken apart. And at the end of the reaction, we make new bonds in our products, okay? And the breaking of a bond, that requires energy. So there has to be some energy put into the system in order to break the bonds. So with hydrogen and oxygen, they'll sit together until someone lights a match and provides that little bit of energy that'll get the first bonds to break. And then when we form the new bonds, at least in this case, the new bonds being in the water molecules, we get a release of energy. And so bond breaking requires energy to break it, and bond formation generally requires or gives energy back. And the net change in energy between those two things is what we're trying to figure out. And we can measure that. That's what we've been measuring as a change in temperature when we look at calorimetry. We've been looking at that net change in energy. But now we're just going to use some theoretical numbers to be able to figure out how much energy there is tied up in these bonds. Okay. So you're going to need information like this, and I'll post a table like this to the classroom. And this is a list of many common bonds, and it tells you the amount of energy required to break those bonds at in a given molecule. So for instance, if we take a look at the HH bond, it takes 432 kilojoules per mole of energy to break those bonds apart. So if you have a mole of these bonds, you're going to need 432 kilojoules. If you wanted to break, let's find the oxygen double bond. So it is, why can't I find an oxygen double? Oh, down at the bottom here. Yeah, O2. So they've listed it a little bit separately here, multiple bonds. And the O2 bond requires 498 kilojoules to break apart. And then you got other double bonds here as well, like the triple bonds and double bonds between nitrogen and between carbon. So down at the bottom here, you've got a list of all of the different double bonds. These are all the single bonds. And then just one to be careful of, in CO2, there is a big enough difference in the energy required to break that C double bond O that we actually measure that number differently. So a regular C double bond O, say in a ketone or an aldehyde, would take 745 kilojoules to break up a mole of that. In CO2, because of the interactions with the other atoms, it takes 799 kilojoules to break up a mole of C double bond O bonds, just in CO2. And CO2 is a very common product and a common reactant. So we have that listed here separately to make our estimation just a little bit better. Okay. Now all that data basically runs through this formula. So you can calculate the enthalpy of a reaction by doing the following. So the triangle again is delta, so change is what delta stands for, change in the enthalpy of reaction. The little r down here just means we're looking at a reaction. The little knot, the little symbol there, means that we're considering this reaction happening at standard temperature and pressure conditions. Whenever we look up data, we're going to use data now to calculate these bonds, we're going to look up that data at standard temperature and pressure. So when you're working at that temperature and pressure, you can put this little knot symbol here. If you don't know what temperature and pressure you're working at, then leave that knot off. And it's whatever you calculate is for those reaction conditions, not necessarily at standard pressure. Right? This little funny E shape means the sum of. So we want to take the sum of all the enthalpy changes required to break bonds, and we want to subtract all the enthalpy changes required or that happen when bonds are formed. So it's the sum of the enthalpy of the bonds being broken and the sum of the enthalpy changes in the bonds being formed. Okay, so that's a formula. Just got to memorize that. That's something to keep in your toolbox. When we do this, if we do this correctly, in exothermic, the sum of the energies will be a negative enthalpy. So in this one we're looking at now, we've already looked at the graph of it. We should be getting a negative answer if we do this question out. And if you do an endothermic, then the sum of the energies will be a positive value. So that's exactly what we've been talking about already. The sign will tell you in the end whether it's an exothermic or endothermic reaction. Okay, so I've got a sample calculation here we can do using bond energy. So let's work our way through that. Before we start the actual calculation, we should make sure that this equation is balanced. And if we have a look at it, it's not. We've got the wrong coefficients here. So just checking it out, I would put I think a 2 in front of the water. So this one's going to need a 2, and that'll let me balance out the 4 H's. And then that'll give me 2 O's here and 2 O's there. So I'm going to need a 2 over here as well. So that I think balances it now. 1C, 1C, 2 O, 4 O's, 4 O's, and 4 H's. Yeah. So now that we have a balanced equation, we can take a look at what's going on in the equation. And we don't only need these coefficients here, the 2's and the 1's. We actually need to know a little bit more about what's going on in the molecule. So for instance, inside of the methane molecule, we need to know that there are 4 CH bonds. It's not one CH bond that has to be broken. For every molecule, there's going to have to break 4 CH bonds. So where we might have 1 mole of CH4, we're going to have 4 moles of CH bonds. Okay. In the oxygen, we need to remember that oxygen is a double bonded molecule, so O double bond O. So there's only one double bonded O, but there are 2 of them required in the balanced chemical equation. So that means we're going to have 2 moles of O double bond O to break. CO2, the coefficient here is 1, but inside the CO2 there's a C double bond O and another double bonded O. So there's 2 C double bond O bonds inside of CO2. So that means again we have 2 moles of C double bond O. And then finally in the water, we have an H and an O and an H. So there are 2 OH bonds in every water molecule, and we need 2 moles of it to do the equation. So that means we have 4 moles of OH bonds that have to be remade, okay? So on this side, we're going to be breaking apart these bonds. So we'll figure out how much energy it takes to break these apart. And on this side, we're going to get energy back. So we're going to make some bonds and we're going to get some energy back, and we'll see how much energy we get back when we make those bonds. Okay? But that bit of thinking has to happen first, or you got to be very clear on what kind of bonds are inside the molecules. Okay, so we're going to use our formula that we just were introduced to, which is this one. And just to write it out in a bit of detail here, let me grab a pen. So we're going to sum up all of the energies of the bonds broken. Well, we've got to take whatever energy there is for 4 moles of CH bonds, and we also have to break 2 moles of O double bond O. So that's the first thing that we have to do, is figure out how much energy does it take to break those apart. And then once we have those broken apart, let's take a look at what we got to make. So we're going to get some energy back because we're going to make 2 moles of C double bond O. Oops, sorry, wrong bracket. 2 moles of C double bond O plus 4 more moles of O-H. And then you can go to your table and you can start to look up numbers for each one of these things. Okay, so I'm going to grab the table and just take a look here. We're going to find CH, the number is 413. So that we can just start filling in this line again. It's going to be 4 moles times 413 kilojoules per mole. plus 2 moles of oxygen. And we go back to the table and find O double bond O, it's 490H. So 2 moles at 498 kilojoules per mole. And we'll add that all together. On the other side, we will subtract 2 moles times the C double bond O, and it was in the molecule of CO2. So we have to use this number down here, 799 kilojoules per mole, plus 4 moles times and whatever an OH is worth. So we'll go back one last time and find OH right there, 467. So that's 467 kilojoules per mole. Okay, and you crunch it through your calculator, and you get, it adds up to 2648 kilojoules on the bonds broken side, and 3,466 kilojoules on the bond formed side. So when we subtract those two numbers, we end up with 818 kilojoules with a negative sign out front. So the negative would tell us that this is an exothermic reaction, and the 818 tells us the magnitude for that reaction. It doesn't have moles on it any longer because we multiplied through by all the moles that were in the equation. So it's 818 kilojoules for this reaction as written. Okay, so it's only for this reaction as written minus 818 kilojoules. Now that could be per mole of methane because there is a 1 in front of the methane, or per 2 moles of oxygen, or per 2 moles of water. You can specify which one you're using here. Probably because this is a combustion reaction, we'd specify this in terms of the methane. So we probably could say minus 818 kilojoules per mole of methane. But for now, we'll just leave it at minus 818. And we see that it's an exothermic reaction. Okay. All right. Let's just take a look at one more, and then we'll wrap this video up. This one's about barbecue fuel. And you might as well give this one a try if you haven't tried any of them in the book yet. This might be a good one to start with. And you're going to take barbecue fuel, which is propane, C3H8, and you're going to compare it to natural gas, which is methane, CH4. And so we just did the numbers for methane. When we burned methane, we saw that we got 818 kilojoules for every mole of methane that we burned. We need to do the same calculation now, but do it for propane, and then compare those two. It would like to know which one of these is better. So it says here how many moles of natural gas are needed to produce the same amount of energy as 1 mole of propane. Kind of makes sense that there would be more energy in the propane because there's more bonds to be broken. So we need to get that number for propane first. So you're going to do the same thing we just did. Let's just get the reaction down, and then we can leave it, and you can go ahead and see if you can do the calculation. So just to get you started, right, it's going to be C3H8 plus oxygen. So just the same thing we did with the methane because we're trying to burn it again. And it's going to make CO2 and water. We're going to assume complete combustion. But now we've got to balance this thing again. So we realize there's 3 C's here, so that's going to need a 3 right there. 3 times 2 is 6, and that's well, that gives me 1 there. Let's not look at those yet. There's H's here, there's 8 of them, and there's only 2 here, so I'm going to need a 4 right there. 3 times 2 for the oxygen is 6, plus 4 more is 10. So it looks like I can get away with a 5 over here. So I think that works. 3 C's, 8 H's, and 10 O's. Yeah. So there's your equation. Now you got to figure out the bonds, run it through the formula, and see what number comes up. And I will post a written up answer of this in the section for this week at a glance. So good luck on that, and we'll get back together again on another topic.